In this video, we discuss evaluating definite integrals by substitution. So in the last video, we were finding antiderivatives by substitution, but now our functions have bounds, or excuse me, our integrals have bounds. So this is going to give us a finite number, and we'd like to find that finite number. The process is very similar to that antidifferentiation by substitution process, but now we need new limits of integration as well. So this problem is very similar to one of the problems that we solved using in the anti-differentiation by substitution section, but we have bounds now. So we said I've got sine of x times the square root of cosine of x plus 2. So that means my cosine of x plus 2 is my inside function. It's nested inside that square root function. So I'm going to let u equal that inside function. And we know that this u substitution will work because when we take the derivative of cosine of x plus 2, we get negative sine of x. So du is negative sine of x times dx. So we look at this and say, can I write everything in terms of u? I sure can. Do I have a negative sine of x dx? I don't have the negative, but I do have the sine of x dx. So I can multiply both sides of this by -1. So sine of x dx turns out to be -1 times du. And this integral can be written as the square root of u times sine of x dx, and sine of x dx is -1 du. I'll put the negative out front and the du on the far right. Sorry, there's something wrong with the camera. All right, there we go. So I say to myself, do I have a rule for that? I do if I rewrite that square root as a 1/2 power, but we need new bounds as well. The integral of this function from x equals pi over 6 to x equals pi is equal to an integral involving u, but I need my bounds to involve or to be values of u as well. So I need to start from u equals some number to u equals some other number. So to do that, to figure out what those bounds are, it's actually really simple. You just plug in the original bounds to this function and you'll find new bounds for u. So I need a new upper bound. So we're going to evaluate u at pi. So I have cosine of pi plus 2. And remember, cosine of pi is -1. So we have -1 plus 2, which is 1 as our new upper bound. And we also need a new lower bound. So we have u evaluated at pi over 6, which is cosine of pi over 6 plus 2. And cosine of pi over 6, well, pi over 6 is a 30-degree angle. So this is a 30, 60, 90 triangle. The side opposite the 30 is a 1 when the hypotenuse is 2, and the side opposite the 60 is a square root of 3. So the cosine of pi over 6 is the adjacent side divided by the hypotenuse. That's square root of 3 divided by 2. And we're adding 2. Now, if I want to get a common denominator, I'll multiply this one by 2 over 2. And I see that my new lower bound is the square root of 3 plus 4, all divided by 2. Okay, so I'm integrating from 4 plus square root of 3 divided by 2 to 1. And that's what we have. Now, if we want to, since this lower bound is actually greater than 1, we can flip this as long as we multiply the resulting integral or the integral by -1. So rather than integrating from this value to 1, I want to integrate from 1 to 4 plus the square root of 3 divided by 2. And that square root of u I want to write as a u to the 1/2 power. So this integral turns out to be equal to that integral. So we'll take the antiderivative, adding 1 to the exponent and then dividing by the new exponent. 1/2 plus 1 is 3/2. Dividing by 3/2 is the same as multiplying by 2/3. And then we evaluate from u equals 1 to u equals 4 plus the square root of 3 divided by 2. Now, some students really want to back substitute. They want to write this in terms of x and then substitute the original bounds. But we don't do that since we've already written the integral entirely in terms of u. We'll just substitute the upper bound for u, substitute the lower bound for u, and subtract. And this is what we'll get. I'll factor out the 2/3. That's 2/3 times 4 plus the square root of 3 divided by 2 raised to the 3/2 minus 1 raised to the 3/2. And anytime you have something raised to the 3/2, like x to the 3/2, I always think of that as x to the first times x to the 1/2, because 1 plus 1/2 is 3/2. That's x times the square root of x. So when I see this, I'm thinking that's 3/2 times 4 plus the square root of 3 divided by 2 times the square root of 4 plus the square root of 3 divided by 2. And we're subtracting 1 from that. If you want, you could try to simplify it further, but I don't think it really simplifies that much. If you distribute this 2/3 to this term, the 2's cancel, but then you end up with a 2/3 over there. So I really don't think it's that much simpler. But you might have something that looks like this. As your final answer. And I'm not sure what that is numerically, but that is sort of an area. We'll find out what that is numerically when we go to desmos.com. Now, one thing that I want to show you, and this isn't something that I've spent a lot of time looking at, but when we make this change of variables, we're taking this area that is between this function and the graph, or the graph of this function, excuse me, and the graph of the x-axis, that's y equals 0, and the vertical lines x equals pi over 6 and x equals pi. That area, what we're saying when we do this u-substitution for a definite integral, is that area is equal to this area. So we take the integral from 1 to this number, so u is starting here and ending here, and we're looking at the square root graph, and we're saying, well, what is the area under the square root graph from 1 to this number? It turns out that that area is this, and the area under this function on this interval has the same value. So let's look at that on Desmos. I always think about that. It doesn't seem that cool when you're talking about functions of one variable, but it's really neat when you see the 3D version of that. So I like to sort of preview that because we do something similar in Calc 3. So when we evaluate this integral on desmos.com, they give us an answer of 2.568 approximately. I'm going to type that answer that I just found. It was 4 plus the square root of 3 divided by 2, no wait, divided by 3 after we simplify, times the square root of 4 plus the square root of 3 divided by 2 minus 2/3. Oops, that should be outside of the radical. Yep, they're the same value. So our answer is correct. I'm going to write that on my paper. Approximately 2.568. So that's the area there under the curve. Now, if you want to, you can do a bunch of calculations on Desmos. Rather than looking at that area, I might look at a different area. So here we do a lot of the calculations that we just did. We said u is the inside function. The outside function is the square root of x. So we find our upper and lower bounds. U at pi over 6 is the new lower bound, and it's approximately this. We get 2 plus the square root of 3 over 2, which is equal to this 4 plus the square root of 3, that quantity over 2. And show that those are equal. And then u at pi is just 1. So the integral that we're looking for when we write everything in terms of u is that -1 times u to the 1/2. The integral of -1 times u to the 1/2 from this bound to this bound. If we flip the bounds, we get rid of the negative and we still get that 2.568, which is what we were expecting. Now, if we wanted to, we could evaluate using basic antiderivative rules. So we add 1 to the exponent and divide by the new exponent, substitute the upper value, substitute the lower value, and then subtract those upper and lower bounds, and we get the same answer. So how can we visualize that? Well, here's our function. It's just a square root function. We're interested in that area right there. And the claim is that that area is that 2.568. So somehow that area from 1 to 2.86, which was that 4 plus square root of 3 over 2, is related to this other area. They happen to be the same. That teal area is equal to the green area. All right. I thought that was kind of cool, but not really necessary. Let's go back to our paper. Okay. So we've got, that was one of our definite integrals. But here's just the process. Here's the process. You identify the inside function, compute du, you write the integrand entirely in terms of u. Then you get new bounds by plugging in the old bounds to your formula for u. Then you've got that integral. Then if you have a basic rule to evaluate the antiderivative, you evaluate the antiderivative, you plug in the upper bound, you plug in the lower bound and subtract, simplify as much as possible. And that's it. That's how we do antidifferentiation by or integration, excuse me, which is evaluating a definite integral by substitution. Now, if we want, we can evaluate another definite integral. We've got the integral from 1 to 9 of 1 divided by the square root of x times the quantity 1 plus the square root of x squared with respect to x. You might say, do I have a rule for that? And I think the answer is no. Got a quotient. The only quotient rules that we have where the integrand is a quotient are these guys. And none of these really look like that because you've got that sort of, it's almost a polynomial expression squared, but that's an x to the 1/2 instead of x to some non-negative integer power. But you've got this sort of almost this binomial type expression, and then you're multiplying by that square root of x. I think if we expand it and multiply by the square root of x, it's not going to get any simpler. But we might be able to use u-substitution. So we're looking for a function nested inside another function. And one of the big indicators for that is a set of parentheses. So if you see parentheses and there's something inside it other than an x, that's probably your u. If you see a square root in the problem, or a fourth root, or a third root, or any kind of root, and you see a function inside there and its derivative is outside, or a multiple of the derivative is outside, that's probably your u. You're just looking for something, one function nested inside another. If you've got a trig function, if you've got something other than an x inside, that might be your u. If you've got an exponential function, if you've got something other than an x inside, that might be your u. Excuse me. So now I've got this expression squared. Since that's in parentheses, I'm thinking that's probably my u. So I'm going to let u equal that inside function. And before we take the derivative, it's helpful to write that as x to the 1/2, right? And then we'll compute the derivative using the power rule. The derivative of 1 is 0. The derivative of x to the 1/2 is 1/2 of x to the 1 less power. So 1/2 minus 1 is negative 1/2. Now you can rewrite that as 1/2 times 1 divided by x to the positive 1/2 power. And x to the positive 1/2 power is a square root of x. So we've got 2 times the square root of x right here, dx. Now you say, do I have a factor of 1 divided by the square root of, or 1 divided by 2 times the square root of x, dx? I don't, but I've got a 1, or 1 divided by the 1 times the square root of x times dx right there. So I don't need this 2 in the denominator. I can easily get rid of it if I multiply both sides of this equation by 2. 2 times du is 1 divided by the square root of x dx. So this can be replaced by 2 du, and that is a u squared, but don't forget, it's in the denominator. So we're going to have the integral of 1 divided by u squared. And this 1 over square root of x times dx is 2 times du. So you can bring the 2 out front and write the du on the far right. Say, okay, do I have a rule for that? Not quite, but I can bring that up to the numerator and then I will have a rule for that. But we need more information. We need bounds. We need to evaluate this function u at x equals 1 and x equals 9 in order to find out what our bounds are for u. If you wanted to, you could just write u evaluated at 1, going from u evaluated at 1 to u evaluated at 9. That's another way that we can represent that expression. You say, okay, well, what is u evaluated at 1 and what is u evaluated at 9? So we do u of 1 and u of 9. U of 9 is 1 plus the square root of 9, which is 1 plus 3, or 4. And then if we evaluate u at 1, we have got 1 plus the square root of 1, 1 plus 1, which is 2. So this integral becomes 2 times the integral from 2 to 4 of u to the negative 1/2, or u to the negative 2, sorry. As you're bringing that 1 over u squared, you're bringing that u up to the numerator so that we can use the power rule. Say, okay, do I have a rule for that now? Yes, I certainly do. So we bring the 2 down, we add 1 to the exponent. Negative 2 plus 1 is negative 1. And then we divide by the new exponent, and then we add c. This becomes negative 2 times a u to the negative 1 is just 1 divided by u, right? And then we add c. Oh, shoot, we don't add c. We're going to evaluate this from u equals 2 to u equals 4. All right. So we've got negative 2 divided by u, evaluated from u equals 2 to u equals 4. So we're going to have negative 2 divided by 4 minus a negative 2 divided by 2. So you end up with 1 minus 1/2, which is 1/2. And that's our area. Now, if we want to, we can look at these areas online and see that the area bounded by this function on the interval from 2 to 4 is equal to 1/2. And that similarly, the area between this function and the x-axis on the interval from 1 to 9 is also 1/6. I think I just explained that whole thing myself, and then I started recording. Sorry about that. I guess you guys didn't know that until I told you. So here is the original function, f of x. If we evaluate the integral, we get 0.5. This is what the region looks like, and that's what the original function looks like. So we're finding the area under the curve for f of x equals this function involving all the square roots and everything from x equals 1 to x equals 9. It turns out if we evaluate the integral using Desmos, we get an answer of 1/2. Now I wanted to show you that we also get an answer of 1/2 if we evaluate the integral from 2 to 4 of that function of u with respect to u. And then we can visualize that area as well. This integral, which represents this area, is equal to this other integral, the integral of this function, h of u equals 2 divided by u squared, from u equals 2 to u equals 4. So that area under that curve is equal to this area under this curve. We see we get the same thing either way. Now, if I'm trying to evaluate this first integral, so we see it and it looks like this. We say that looks way too complicated, I can't do it. But if I do the u-substitution and I write it like this, or even better, if I write it like 2u to the negative 2, then I can say, okay, I just use the power rule. We compute the antiderivative. I'll call that capital H of u. So we add 1 to the exponent, divide by the new exponent, and then we substitute in the upper bound of 4 and the lower bound of 2. And we get that 1/2. So we see that it's very simple to apply the fundamental theorem of calculus to this integral, whereas it's hard to write the antiderivative to this. So we've got u-substitution, which allows us to write that integral in a form so that we've got a basic rule for it. And then once we have that antiderivative, we can plug in the, we can get new bounds for u. We can find that u at x equals 1 is 2, and u at x equals 9 is 4. And then we evaluate this definite integral in terms of u just using our basic rules. All right, so let's look at our paper and do our last example. All right, so that's what we have. Oops. And then here's our last one, last example. And the integral from negative pi over 2 to pi over 2 of sine to the 4th of, let's do just x, that's fine. times cosine of x dx. Now you might say, oh, they're trig functions. I don't see anything for u-substitution. I'm looking for a function nested inside another function. I don't know why I put that x in parentheses. Sorry about that. And say, well, there's actually some implied parentheses there. Anytime you see a trig function raised to a power like that, what that means is that original trig function is inside the parentheses. Sine of n, or sine raised to the nth power of x is sine of x, all raised to the nth power. So if I've got this sine to the fourth of x, what that means is that we're just taking the sine of x and we're raising it to the fourth power. That's actually usually how I say it. Rather than saying sine to the fourth of x, I would say sine of x to the fourth power. When I write it like this, it's a lot clearer what our u-substitution should be, because we're looking for a function nested inside another function. And one indicator of that is parentheses. We see parentheses, what's inside the parentheses might be our u. If we see a square root or a radical, what's under the radical might be our u. Whenever we see exponents or trig functions, if there's something inside the trig function other than an x, like a function of x that's more complicated, then that might be our u. In this case, we've got a trig function inside a power function. So I've got sine of x raised to the fourth power. So that is probably my u. So I'm going to let u equal sine of x. And then I know that will work if I compute du and a multiple of du is up here. So we're never really sure it's going to work until we compute that derivative. Sometimes do it in my head. This time I know it's going to work. What's the derivative of sine of x? We know it's cosine of x, right? So du is cosine of x dx. So this is actually du, and this piece is u raised to the fourth. That 4 is still there. So now I've got the integral of u to the fourth du. That's a simple one. It's just a power rule, right? So the integral of this is going to equal the integral of this, but we need new bounds for u. So we need to figure out what u is when x equals negative pi over 2 and x equals pi over 2. Those are going to be our bounds for u. So we're going to have the integral of u to the fourth from u evaluated at negative pi over 2 to u evaluated at positive pi over 2. Say, well, sine evaluated at pi over 2 is 1. And sine evaluated at negative pi over 2 is negative 1, I think. Let's look at the graphs. So sine looks like this. At pi over 2, we get a 1. At negative pi over 2, we get a negative 1. So those are our values. So we're actually evaluating the integral from negative 1 to 1 of u to the fourth with respect to u. That's easy enough to do. Just use the power rule, add 1 to the exponent, we'll get 5, divide by the new exponent. Substitute the lower bound and the upper bound and subtract. So we're going to have 1/5 times 1 to the fifth minus negative 1 to the fifth. Negative 1 to the fifth is negative 1, so we have 1 minus a minus 1, which is 2. So we get 2/5. And that's our answer. So let's look at those graphs on Desmos, and then we'll be done. So, okay, remember how this works. Look for an inside function, compute du, write the integral in terms of u. Don't forget to get your new bounds if it's a definite integral. Then this integral is equal to this integral, so the area under this curve is equal to the area under that curve. You evaluate this one using the fundamental theorem of calculus, and that's your number. That's your area or your net area, depending on whether the function is positive or negative. So let's see what that looks like. So here is our function, f of x equals sine of x raised to the fourth times cosine of x. This is what it looks like on the interval from negative pi over 2 to pi over 2. The net area is 0.4, or if we prefer, it's 2/5. That's the answer that we got when we did this on paper. And say, well, that is the same. The claim is that that is the same as the other integral. We had a function of u. We said that that function of u was just u to the fourth, because we let u equal sine of x. if we integrate u to the fourth from -1 to 1, we also get that 2/5. So either way we get 2/5. We can represent that geometrically this way. So this, the area of that region, I'd like it in a different color. There we go. The area of that region between the function and the x-axis is equal to the area of this other region between the function and the x-axis. The first one's kind of cooler. It looks neat. We've got this area plus this area is going to give us that 2/5. On the other one, we have this area plus this area is giving us the 2/5. But we see either way, this transformation by letting u equal sine of x, we've transformed this wave into this new function. And we said that if we do that, we can easily compute the antiderivative using the fundamental theorem and then plug in the bounds to get the area. But turns out, either way, you get the same area. So the integral from -π/2 to π/2 of this sine to the fourth of x times cosine of x is 2/5. And I think that's pretty cool. All right, so that is the end of our lecture over antidifferentiation by definite integrals by substitution. I think we're pretty much done with the course. I might do a video on numerical integration. I almost never cover that in Calculus 1, but it's usually because of time constraints. I think I might make a video at least for the playlist. Let me know if you have any questions about this material. I think it's really beautiful and interesting, especially when you look at the transformations of the graphs. There's something mysterious about those transformations of the graphs, I think. But sort of a preview of what we'll be doing with the Jacobian in Calculus 3. So that's it. I hope you enjoyed the course materials. Let me know if you have any questions.